You think you know what magnetism is, don't you? A piece of iron sticks to your refrigerator. Two bar magnets can push and pull without touching. Simple. A magic rock. Everyone has played with them, so we think we understand. We learn the rule, opposites attract, likes repel. That's it. But here's the problem, that understanding is completely, utterly wrong. It's not just incomplete, it's a lie we tell ourselves to feel comfortable. It's a label, a name, and knowing the name of a bird doesn't mean you know a single thing about the bird itself. What is that invisible force, really? Why do only some metals feel it? What's actually happening in the empty space between the magnet and the nail? If I take an atom, the smallest piece of iron, and split it apart, where is the tiny magnet inside? And if we can find it, why does it exist at all? The truth is, we are surrounded by a silent, invisible push and pull that defies everything our hands tell us about how the world works. And to understand it, you have to be willing to let go of what seems obvious. Let me show you what I mean. You pick up a magnet. It pulls a paperclip. Your brain, being a wonderful pattern matching machine, immediately tells a story. The magnet is sticky. It has a property of attraction, like static cling or glue. And for the paperclip, the story is that it's just a passive thing, waiting to be grabbed. So we give these properties names to make sense of it. We paint one end of the magnet red and call it north. The other end is south. We say the paperclip becomes magnetized. And we have our perfect, comforting rule, north seeks south, north repels north. The world is tidy. The diagram in your old textbook has neat lines of magnetic field flowing from one pole to the other. It's a closed loop. It looks solved. But here is the trap of names. When you say magnetic field, what are you actually saying? You've just replaced one mystery with a phrase. You've said, it works because of the thing that makes it work. That's not an explanation, that's a description. It's like saying a watch works because of its watchness. It tells you nothing. The real question, the physicist's question, is how? How does the magnet reach out across that centimeter of nothing, that perfect vacuum, and organize the atoms in the paperclip? How does it tell the paperclip to move? What is the messenger? You see, we're comfortable with forces that push by contact. I shove a book, the book moves. That makes sense to our 8 brains. But a force that acts at a distance, through empty space? That feels like magic. Isaac Newton himself felt this was absurd when he described gravity. He called the idea an absurdity. So with magnetism, we papered over the absurdity with a pretty diagram and a simple rule. We stopped asking. We accepted the label. But I want to ask. I want to look at that paperclip and not see a passive piece of metal. I want to see a chaotic dance of particles that, when the magnet comes near, suddenly falls into a magnificent, ordered parade. I want to find the origin of the push. Let's start not with the rule, but with a simple observation that breaks the rule. Take that bar magnet. Snap it in half. What do you have? 2 smaller magnets, each with its own north and south pole. Break one of those pieces again? Same thing. North and south. You can imagine doing this down to the tiniest speck. Where does it end? It ends where all true explanations in physics must end, in the heart of the atom itself. That's where our journey begins. Not with the magnet in your hand, but with a single, lonely atom of iron, sitting in the dark. We have to go back. Not to the first magnets, those curious chunks of lodestone the ancient Greeks found, but to the moment we realized magnetism wasn't a special trick of rocks. It was a thread woven into the very fabric of matter, and it was tied, inexplicably, to another thread, electricity. For centuries, they were separate mysteries. One was the silent pull of the lodestone. The other was the frantic spark of lightning, the twitch of a frog's leg touched by 2 different metals. 2 different phenomena. Until 1820. Picture this, a lecture hall in Copenhagen. A professor named Hans Christian Ørsted is setting up a demonstration on electricity for his students. It's a simple circuit, a battery, a wire. He plans to show how the wire gets warm when current flows a known effect. But fate, as it so often does in physics, intervenes. On his bench, by pure chance, sits a magnetic compass. Ørsted closes the circuit. Electricity flows. And he, or perhaps a sharp-eyed student, notices it. The compass needle twitches. It doesn't point to the Earth's magnetic north anymore. It points perpendicular to the wire. He opens the circuit. The needle swings back. Close it, it swings again. Think about what just happened. This was huge. For the first time in human history, someone had made a magnet move without another magnet. They had reached out and commanded the invisible force with electricity. Ørsted didn't just discover a new effect, he discovered a connection. He found a doorway. The two great mysteries of force, the magnetic and the electric, were shaking hands. The news spread through Europe like an electric current itself. In France, a brilliant, intensely mathematical physicist named André-Marie Ampère heard about it. And Ampère didn't just see a curious twitch, he saw a new world of forces. Within weeks, he had done experiments of stunning elegance. He showed that two parallel wires carrying electric current could attract or repel each other exactly like magnets. They didn't need to be iron, they were just copper, alive with moving charge. He formulated a mathematical law for this force. In his mind, he began to theorize, what if all magnetism is just electricity in motion? What if the magnet itself is not a special object, but a collection of tiny, hidden, circular currents? This was the first great leap. Magnetism is not a thing. It is a side effect. It's what happens when electricity moves. Now the stage was set for the thinker who would build the cathedral, a self-taught English bookbinder's apprentice with a mind of breathtaking imagination, Michael Faraday. Faraday saw the world in lines of force. Where Ampère thought in equations, Faraday thought in pictures. He took a bar magnet, sprinkled iron filings on a piece of paper above it, and saw the field, those beautiful, curving arcs from north to south. But he asked a deeper question. If an electric current can create a magnetic field, can a magnetic field create an electric current? For nearly a decade, he tinkered. He tried holding a magnet near a wire. Nothing. He tried a bigger magnet. Nothing. The magnetic field was just there, static. It did nothing. It was like having a waterfall that couldn't turn a wheel. Then, in 1831, the eureka moment. He wasn't just holding the magnet near a coil of wire. He was moving it. He plunged the magnet into a coil. The needle on his meter kicked. He yanked it back out. The needle kicked the other way. A changing magnetic field creates an electric current. This was Faraday's law of induction. It's the principle behind every generator that powers our civilization. The wheel turns because the magnet moves, and its changing field pushes electrons in a wire to flow. Do you see the beautiful symmetry that was emerging? Ørsted, electricity in motion makes magnetism. Faraday, magnetism in motion makes electricity. They were two sides of the same coin. They were linked in a dance. But a dancer needs a stage. What was this field that could curve through space, store energy, and push charges? Faraday was convinced it was a real, physical thing, not just a mathematical diagram. He called it a condition of space. The scientific establishment, steeped in Newtonian ideas of particles and forces at a distance, largely thought he was a charming, unmathematical dreamer. It took a theorist of monumental confidence, James Clerk Maxwell, to translate Faraday's physical intuition into the language of mathematics. In the 1860s, Maxwell took Faraday's lines of force and Ampère's laws and added one critical, brilliant idea of his own. He looked at the equations and saw they weren't quite symmetrical. To make them complete and beautiful, he proposed that a changing electric field could also generate a magnetic field, even in empty space, with no electric current at all. This was the final piece. He synthesized it all into a set of just 4 elegant equations. And when he solved them, something miraculous fell out. The equations predicted waves. Waves of intertwined, oscillating electric and magnetic fields, constantly generating each other as they traveled. He calculated their speed from pure laboratory measurements of electricity and magnetism. The number he got was 299,792,458 meters per second. The speed of light. The shock must have been profound. Maxwell had discovered that light is an electromagnetic wave. The lodestone that pulls your paperclip, the spark from your finger, and the beam from your lamp are all manifestations of the same fundamental force, electromagnetism. The curtain had been pulled back. Magnetism wasn't just a property of special rocks. It was one half of a cosmic phenomenon whose other half was electricity, and whose most famous child was light itself. So, by the end of the 19th century, the stage was set. We knew magnetism came from moving electricity. We knew electricity and magnetism were a unified force. We knew it propagated as waves at the speed of light. But we still didn't know the answer to our most basic, childish question: what is moving inside the piece of iron? To answer that, we had to wait for the next revolution. We had to peer inside the atom and meet a ghost with a spin. All right, so we've reached the atom. Maxwell gave us the stage, the electromagnetic field. Faraday gave us the actors, the lines of force. But who are the dancers? What, inside that silent, solid-looking piece of iron, is actually moving to create a perpetual magnetic field? Let's start simple. Think of an atom. A tiny nucleus, a cloud of electrons whizzing around it. Now, an electron isn't just a little ball. It carries two fundamental properties that matter for our story. First, it has a negative electric charge. Second, and this is the strange part, it has an intrinsic spin. Now, spin is a terrible name. It makes you think the electron is spinning like a tiny planet. It's not. It's a purely quantum mechanical property, a kind of intrinsic angular momentum and magnetism it just has, the same way it has mass or charge. It's a fundamental label. For our purposes, just imagine each electron is a permanent, microscopic bar magnet. Its spin gives it a north and south magnetic pole. Here's the first key. In most materials, these tiny electron magnets are paired up. In a pair, one electron spins up, and its partner spins down. Their magnetic fields point in opposite directions. They cancel each other out perfectly. It's like having two identical bar magnets glued together north to north and south to south. They struggle against each other and produce no net field outside. In a material like wood, plastic, or copper, this is the case. All the electrons are neatly paired and canceled. That's why a magnet doesn't stick to your door. The material is diamagnetic. It weakly repels a magnetic field because the external field slightly disturbs these balanced pairs, inducing a counterfield. It's a tiny effect, but iron is different. Iron is a rebel. Here's where it gets strange. In atoms of iron, cobalt, and nickel, the classic magnetic materials, something special happens in the way the electron clouds are arranged. There's a quantum rule called the Pauli exclusion principle that says no two electrons can be in exactly the same state. It forces electrons in certain orbitals to be unpaired. In iron, there are several of these unpaired electrons, each with its spin magnet not cancelled out. So, in one single, lonely atom of iron, you have a bunch of these unpaired spin magnets. They often align with each other. That means one iron atom, all by itself, is a permanent tiny magnet. We call this an atomic magnetic moment. This is the fundamental unit. The spec you'd get if you could break a magnet down to its ultimate, smallest piece. It's not a pole, it's this atom with its aligned spins. But if every iron atom is a tiny magnet, why isn't every piece of iron a magnet? Pick up a nail from the workshop. It doesn't stick to anything. Yet it's made of billions of these atomic magnets. This is the heart of the mystery. And here's the answer: disorder. In an unmagnetized lump of iron, all those atomic magnets are pointing in random directions. North, south, east, west, every which way. Statistically, for every atom pointing left, there's one pointing right. They all cancel each other out on a large scale. It's a chaotic mob of tiny magnets, fighting themselves into neutrality. So, how do you make a magnet? You don't create the tiny magnets, they're already there. You have to organize the mob. You have to get a large number of these atomic magnets to point in roughly the same direction. And here, nature gives us a helping hand. In materials like iron, there's a quantum mechanical interaction between neighboring atoms, the exchange interaction that makes it energetically favorable for their spins to align. It's not a magnetic force, it's a much stronger, purely quantum consequence of the electron's wave functions overlapping. This causes the atoms to spontaneously form small, organized patches where all the spins are aligned. These patches are called magnetic domains. Think of a domain as a neighborhood where every house flies the same flag. Inside one domain, every atomic magnet points the same way. That domain is a fully magnetized patch of the material. But your nail contains millions of these domains, and each domain's flag points in a different random direction. The north of one domain might point east, the north of another points up, another points northwest. So, the entire nail still has no net magnetic field. It's like a parliament where every faction is shouting in a different direction. No single voice wins. Now, watch what happens when you bring a strong magnet near that nail. You bring the external magnet close. Its magnetic field is like a powerful, commanding voice. It starts to do two things. First, it makes the walls between domains move. Domains that happen to have their magnetization aligned, or nearly aligned, with the external field grow. They consume their neighbors. It's like the faction whose slogan matches the ruler's message gains members. Second, for domains that are stubborn, the external field can force the entire block of atomic magnets within that domain to rotate, like turning a regiment, so they align with the field. This process, domain wall motion and domain rotation, is how the paperclip becomes magnetized. The external magnetic field organizes the chaos. It turns the mob into an army, all pointing their spears in the same direction. Now, the entire paperclip has a net magnetic field aligned with the magnet that induced it. That's why it feels a force. And that's why a magnetized paperclip can now pick up another paperclip. It has become a source of the field itself. But let's pause. This explains ferromagnetism, the strong magnetism of iron. What about the simple rule, opposites attract? We need to descend one more level, from the domain to the field itself. Remember, the fundamental source is a moving charge or an intrinsic spin. Ampere and Maxwell taught us that these create a magnetic field vector, a little arrow at every point in space that has both a direction and a strength. Now, when you have a bar magnet, what you really have is a collection of aligned atomic currents, the electron spins. At one end, these tiny current loops, all aligned, make it so the magnetic field vectors emerge from that end. We call that the north-seeking pole. At the other end, the field vectors converge and go back into the magnet. That's the south pole. The field lines form continuous, closed loops. They come out of the north, curve through the space around the magnet, and dive back into the south, and then complete the loop inside the magnet back to the north. So, why do opposites attract? Bring a north pole near a south pole. Look at the field lines between them. The field lines from the first magnet's north pole are aiming to go to a south pole. If there's a south pole nearby, those lines can take a shortcut. They connect directly. This configuration stores less energy in the magnetic field. Nature likes to minimize energy. The magnets move to lower the energy, and that movement is an attractive force. Now, bring two north poles together. The field lines emerging from each pole are similar. They don't connect, they diverge. To have continuous field lines, they have to curve wildly around each other, stretching far into space. This configuration stores more energy in the field. To reduce this higher energy, the magnets push apart. That's repulsion. The force is not some mystical pull between labels. It's a consequence of the geometry of this invisible field, the electromagnetic field, trying to find the most relaxed, lowest energy state. The rule is just a shorthand for this deeper physical principle. And here's something even stranger. What about a monopole? If you break a magnet, you get two smaller magnets, each with a north and south. You never get an isolated north by itself. This is a profound fact. In Maxwell's equations, there is a beautiful asymmetry. For electric fields, you have sources, positive charges and negative charges. You can have a single, isolated positive charge. The electric field lines radiate out from it to infinity. But for magnetic fields, Maxwell's equations have no source term. There is no magnetic charge. Magnetic field lines have no starting point or ending point. They are always closed loops. They always come back around. This tells us something fundamental about our universe. As far as we know, magnetic monopoles do not exist. Every north is married to a south. You cannot have one without the other. This is a deep difference between electricity and magnetism, two sides of the same coin that are yet not perfectly identical. Let's do a thought experiment to tie this all together. Imagine you could shrink down and stand on the north pole of a bar magnet. What would you see? You wouldn't see a fountain of magnetic stuff spraying out. You'd sense a field, a condition of space that makes a tiny compass needle point directly away from the surface. That field is created by the aligned spins of electrons deep within the magnet, billions upon billions of them. Their combined effect is summed up by a number we call the magnetic moment of the magnet. This field permeates all of space, weaker and weaker with distance, but in principle, extending forever. Now take that magnet and throw it. You are now accelerating a magnetic field. And what did Faraday discover? A changing magnetic field creates an electric field. So, as you throw it, you are actually generating a complex pattern of electric fields around it. And if you could shake it back and forth rapidly, you would launch some of that field away as an electromagnetic wave or radio wave. Your humble magnet is, in principle, a radio transmitter. That's the full, unified picture Maxwell gave us. So, to recap, a magnet works because of the quantum mechanical spin of unpaired electrons in atoms like iron. These give each atom a permanent magnetic moment. In a magnetic material, these atomic moments spontaneously organize into aligned patches called domains. In an unmagnetized piece, the domains are randomly oriented, canceling out. An external magnetic field aligns these domains, creating a net large-scale magnetic field. That field is a real, physical entity, the magnetic component of the electromagnetic field. Forces arise because the field configuration seeks its lowest energy state. And all of this is inextricably linked to electricity and light by the sublime symmetry of Maxwell's equations. We've gone from a sticky rock to the quantum spin of a ghostly particle, through the organization of domains, to the geometry of fields in space, all the way to the speed of light. That's the chain. That's the how. So, why do magnets work? Let's put the chain together, link by link, and see the complete picture. It begins in the quantum realm, with a fundamental property of an electron we call spin. It's not a rotation, but a kind of intrinsic magnetism the particle simply has. In most materials, electrons pair up with opposite spins, canceling this magnetism out. But in iron, cobalt, and nickel, certain electrons remain unpaired. This means a single atom of iron is, by itself, a permanent, microscopic magnet in atomic magnetic moment. These atomic magnets don't like chaos. Through a purely quantum mechanical push, the exchange interaction, neighbors influence each other to align, forming organized patches called domains. Inside each domain, billions of atomic moments point in unison. But in a raw chunk of iron, these domains are like rival kingdoms, each pointing its magnetic banner in a random direction. The result is a civil war that leads to a standstill, no net magnetic field. When you bring a strong magnet close, its external magnetic field acts as a universal command. It resolves the civil war. Domain walls move, and whole domains rotate, until a significant majority of those atomic banners are flying in the same direction. The material is now magnetized. The chaotic mob has become a disciplined army. This army of aligned atomic spins creates a large-scale magnetic field. This field is not a metaphor or a diagram. It is a real, physical entity, the magnetic component of the electromagnetic field. It fills the space around the magnet, a condition of space as Faraday called it, capable of storing energy and exerting force. The force to push or pull you feel arises from this field's geometry seeking its lowest energy state. When a north pole meets a south pole, the field lines connect directly, creating a low-energy configuration that pulls the magnets together. When two north poles meet, the field lines are forced into a high-energy, repelling configuration. The rule opposites attract is thus a shorthand for a deeper truth. Nature minimizes the energy stored in the magnetic field. And this magnetic field is never alone. It is forever entwined with its other half, the electric field. A changing electric field generates a magnetic field, as in Ørsted's wire, and a changing magnetic field generates an electric field, as in Faraday's moving magnet. This mutual generation is the dance described by Maxwell's equations. The ultimate consequence of this dance is that disturbances in this coupled field propagate as waves, electromagnetic waves, at the universal speed limit, c. The magnet on your fridge is a static manifestation of the same force whose dynamic, oscillating form is the light by which you see it. Therefore, a magnet is not a special sticky object. It is a bulk manifestation of quantum order. It is a testament to a deep principle. Large-scale, seemingly magical forces emerge from the collective behavior of countless tiny components following quantum rules. The force you feel with your hand is the summed effect of trillions upon trillions of electron spins, organized into domains, creating a field that obeys the relativistic symmetry of electromagnetism. The simple children's toy contains within it the secrets of quantum spin, statistical order, classical field theory, and relativistic invariance. It is a portal through which you can touch, with your own fingers, the elegant and layered architecture of physical reality. You aren't just holding a rock that pulls on metal. You are holding a knot where several of the universe's most fundamental threads are tied together. This is the thing about physics. It's not about giving you comfortable answers. The comfortable answer was opposites attract. It was simple, it fit on a bumper sticker, and it explained nothing. It made the world seem like a collection of labels and rules. The truth is always Messier, and always more beautiful. The truth takes you on a journey from your hand, down into the heart of the atom, to meet a spinning ghost of a particle. It shows you how chaos can be organized into order, and how that order projects a field into the emptiness of space. It ties that field to electricity, and then to light itself. The truth connects the quantum jitter to the classical push, all governed by equations of stunning symmetry. When you understand that, the magnet is no longer a simple thing. It becomes a story written in the language of fields and forces, spins and domains. It's a testament to the fact that the universe is not just stranger than we suppose, but stranger than we can suppose. Our common sense is a tiny raft on an ocean of counterintuitive wonder. So, the next time you feel that click, that pull between two magnets, remember, you are not just feeling a force. You are feeling a direct consequence of the structure of the universe, whispering its deepest secrets through iron and space. And that whisper tells us that beneath the surface of the simple lies the sublime. That's the beauty of physics. Not comfort, not simplicity. Truth.